The other two are stereochemistry handouts. Stereochemistry will be coming next week. So I'm getting you those today. Next week in lab, Monday, Tuesday, recrystallization. There's a video for that, yeah. That lab is not too long. We will have some lecture time before lab down here at 2:30 each day. Lecture time. Okay, do Monday your literature assignment, lab literature assignment, yeah? Question?
Are you doing a report for the lab
Unknown lab report?
on Monday?
When it's due.
We'll say that will be due when you come to lab on Wednesday, Thursday. Okay? I think that will be okay. I think. Unknown lab. Some of you are not signing in or out of lab. You should be doing that. Okay. Let's get started. We were looking at anti-addition of halogen to alkenes to get bisphenol dihalides. Any other questions before we get started? Good to go? Good to go? All right, let's make some progress here. Lots of alkene reactions to cover. Mechanism for addition of halogen to alkenes. Polarizable, we can attack one, kick the other off. Okay? Where are we going to make cation at? Left or right? Left or right? Obviously left, correct? Yeah? Okay. What can happen next? Again, if this chloride here attack that cation and they bond, we get product. Chlorine carbon. That's product. That's not the mechanism, because the closest electrons in this cation is the chlorine that was just added. Okay? It's closer. That's back bonding, I call it. Okay? And so B is the pathway, not A. And when it back bonds, this chlorine makes bond, and you have to have a three-membered ring, and the chlorine is now positive. Okay? Now what letter are we under on the green sheet? We're under what here? B? And what does B say? I underlined it. Without carbocations. No carbocations. So what is this? Carbocation. That line says no carbocation. That's because this is not actually formed. And this is the way I do this. I present it like this. NAF, not actually formed. Okay? Why am I showing it? I show it because I think it's the best way to show it, and I think it helps you see what's going on. It's not actually formed. The first intermediate in this mechanism is the chloronium ion. It's called. We've got the bromine, bromonium ion, etc. We'll come back here. At this point, to get the final product, that chloride, instead of attacking here, it actually attacks this carbon here, which that chlorine is back bonded to. Can we attack a carbon and kick off a so-called leaving group? Yes, that's on the other sheet. There's two ways to attack a carbon. We can attack a carbocation, and we know we attack it from either side, right? Or we attack a carbon and kick off a leaving group. Yeah? Okay? Right here. Attack a carbon, kick off the leaving group. This is probably the most important page for this course. Okay? You've got to master that right there if you want to move ahead. Okay? This mechanism, not here, it attacks here and kicks this chlorine off that back bonded, and that gives final product because this chlorine is now bonded to this carbon. And this opens up, well, it's still bonded over here. That's the product, chlorine bonded to each carbon. We call it a backside attack by the chloride because when you attack a carbon and kick off a leaving group, how do you attack? You attack backside, opposite side. Okay, here's the leaving group, right? Where are you going to attack? No, that's front side. Backside, kick off. Backside, how are you going to attack? Back. No, that's front side.
Okay, backside.
Backside. Backside refers to behind the group. Okay? Over here, attack, kick it off. Okay? You do not attack front. Why? Because the group is in the way. Back here, you attack. Okay? When you kick something off, you attack backside. Again, it's on the sheet. We call that backside attack by the chloride right here. Okay? Importantly, it could attack over here and kick the chlorine off of that. Why does it attack over here? Well, that's explained over right here. There's more partial positive here. Okay? Because this is best. This is a strain, 3-membered ring. Ring strain, right? Also, the chlorine has a positive charge, which chlorine doesn't like being positive. So you might ask, why did this even come over here and make this strain ring and become positive? Why did it even do it? Well, it is making a bond. And bond is a good thing. And we know from physics that electrons, which are minus, like what? Positive. So it can't help but be attracted to it. That doesn't mean it likes it. It would love for something to come in here and kind of kick it back off and go back to neutral chlorine. But over here, so this ring is a little bit strained. This is sort of back bonding. This is showing sort of the lone pair associating over here, but it's a weak attraction. Or you could show a weak attraction the other way. Which way is best? Well, this, because really, it's like a partial positive here. Would you rather have a partial positive on that carbon or this carbon? Well, the answer is here, because this has 2 rich friends. And so that can handle being positive compared to over here. So the strained ring, this bond is really quite weak. There's a lot of partial positive here. More substituted. That's the reason there's more partial positive there. And so when this chloride comes in here, okay, it's in here, it's coming in here, it's like, oh, this one's more partial positive. And so it's attracted over there, it attacks over here and kicks that off. This is important as we move forward. Reason why we'll see moving forward. Here's the mechanism. Okay, there's different levels to this. First off, can we just predict products? Take this alkene reacting with bromine, what are you going to get? This is actually one of the easiest reactions we'll ever look at. What happens here? Just in terms of predict product. Don't you put a bromine on each carbon of the original alkene? That's it. Isn't that what we did above? What did we do above? Didn't we end up with a chlorine on each carbon of the alkene? That's easy as apple pie, right? But mechanism, though, very important. We'll learn when we have to consider stereochemistry. What about this here? This is called an interhalogen. You're more commonly going to see Br2, Cl2, I2. This is a mix called interhalogen. It'll react the same way, same mechanism, but we have to figure out, does the alkene originally attack the iodine or the chlorine? Well, up there we said the chlorine becomes polarized by, induced. This down here is already polar. It has a permanent dipole. Which halogen is electrophilic? Chlorine's more electronegative. Electrophilic means which one's more partial plus? Yes, partial plus, partial minus. The iodine is electrophilic. Iodine is the one that's going to want electrons to come. The other way you can say that is electrons are attracted to electrons. So this attacks iodine. So this is going to swing out like this. Somebody pulled the pin out here. Pull away, you go make bond to iodine. Yeah? Go make bond to iodine, leaving this as plus. Does that seem consistent? But this, when we do this, this chlorine gets kicked off. That's really an attractive a kickoff, leaving group. We make that plus Cl minus. Yeah? What's the next step? First off, let's go back and clarify this. This is not actually formed, is it? In the mechanism up here, how many intermediates did I have? There's only one intermediate. It's right there. Let's talk about this more. I say not actually formed. There's no carbocation here. These two steps are actually concerted. What does that mean? Happen at the same time. Yes. Okay, here it is. I'm an alkene and you're a chlorine. You're actually bonded to the other chlorine. Alkene. And then somehow then induce dipole here and you become partially positive, something. By the way, that can happen a number of ways. What happens? This comes an attack and kicks you off, right? Did we do that up top? Very top left corner. Attack one chlorine, the other one gets pushed off. Okay? Here. And what does this become? This used to be the alkene. This over here became a carbocation. But it's not actually formed because you have a lone pair. Okay? You see B, the new chlorine has a lone pair I circled. This is what happens. As soon as I am attacking you, you come back with your lone pair and attack over here. There it is. We go straight to the three-membered ring. Okay, let's do it again. This time let's do the transition state. As soon as I attack you and you participate, you're bonded here. You need another arm. Just stick your arm forward like you're bonded. You got. This is your lone pair. Bring your hand over here. Okay. Here we go. This way. As soon as I attack you, you're attacking you. Boom. Three-membered ring. Okay. It all happens at the same time. As soon as this attacks the chlorine, that chlorine is really back bonding. Now books may show it like this. Right there. As soon as that's coming out to attack the chlorine, the lone pair is coming this way. But I find that this leads to too much confusion early on, and I don't see what's going on. I'm trying to show it to you stepwise, even though it's not stepwise. It also reinforces the fact that, okay, where would cation be? Here. Everybody agree we make cation here and not over there? Where are we going to make cation? Left or right? Left. Okay. But guess what? This is also the same place. This chloride attacking here, it eventually attacks there, right there. The problem is it doesn't attack a free cation. It attacks the same spot, but it attacks backside, and that's going to be important on the next page. So this right here tells you where the next chloride is going to attack. It's just a different rationale over here. Cation is more stable because of rich friends, more positive here because of rich friends. Okay, so let me ask you, is this really formed, or what's going to happen at the same exact time? This is not actually formed, because what happened at the same... As soon as this attacked the iodine, what was the iodine lone pair doing? It was coming this way. Same exact time. That's not actually formed. And we get to... There's 3 membered ring, 2 lone pairs left. That iodine is now positive. Now, you do not have to show this if you do not want to, because it's not actually correct. But I think it's the best way to do it. I think it's going to make your life easier. It's the explanation that I give you. Okay? Books are not going to show this. Here's our first intermediate. What happens next? Now the chloride comes in. Which carbon is it going to attack? We can attack that one and kick the bond off of there, or we could attack there and kick the iodine off of there. Which one? Well, it's already answered over here. Where would you rather make more partial positive? Right here, because it has a rich friend. And again, you end up attacking the same place as if it attacked there, but you don't attack the free cation. You attack something and kick off the back bonded iodine, and this comes in here, kicks that off, and what's the product? Everything's now bonded together. This is going to give... Which halogen is on the N carbon here? Iodine. And the chlorine is on the second carbon. There's your product. Understanding mechanism allows you to understand iodine is going to be on the N carbon and the chlorine will be on the second. See, up here you didn't have to worry about that. We put a bromine on each carbon. You didn't have to think. Bromine's bromine. But down here you had to think more mechanistically. You had to think about the initial polarization of our reactant there. And we would say that this reaction is regioselective. That is, the chlorine is going to be bonded to that carbon, that region, or that site. Site selective, maybe sounds... Okay? Will we get this product? No. These are called regioisomers. Regioisomers are just constitutional isomers, but it's in the context of a reaction. Will the iodine end up bonded to this region or this region? That's, okay. Well, it's going to bond to this region, again, that site. Everybody understand when I say site selective? It seems better. But the term is used regioselective. How do we know that this is the mechanism? How do we know it's back bonded? Well, largely because of stereochemistry. Stereochemical alkene. If you take this alkene, cyclohexene, and react it with chlorine, you will only get, you'll have a chlorine on each carbon, okay? But they will only be trans to each other. They will not be cis. Now, our mechanism should explain stereochemistry. If the mechanism involved a true carbocation, that is, if we attack the chlorine, where would we make cation, top or bottom? Either. Either. It's a symmetrical alkene. Either is the same. There's no preference. I showed it at the top. Now the new bond at the bottom, that carbon is now tetrahedral. Both sp2 here. So we've got to show bond forward or back here. I showed it forward. If that's a cation, and the chloride just attacks there, how's it going to attack, from the front or back? How do you attack a free carbocation? Either side. It would be front or back, wouldn't it? 50-50. That's how you attack a carbocation. Thus, the product would be, wouldn't it be both of these? I mean, that's the same. Wouldn't you have some where the chloride came in from the front, and then some where the chloride came in from the back? If you attack a free carbocation, you should get both cis and trans. But we know when you do this in the lab, you do not get cis. You only get trans. So that doesn't make any sense. Same way over here. Because up here, you could actually attack, and this could be back. But if you attack a free cation, well, that would be back in both cases. Up here, you would have either front or back. But again, you would have trans and cis. But we know we don't get cis. So that mechanism is faulty. The true mechanism is backside. I don't think it's shown. Backside attack. That is, this is not actually formed. I'll come from here. Physics tells us, and just proximity, this is going to attack here, right? That happens instead, and what does that lead to? Leads to a ring. This bond is forward. This is now bonded here. How's that bond going to be? No, think about it. It has to be forward. Here's the board, and the lower chlorine is forward. If it's forward, and then that makes bond over there, how's the other bond going to be? It has to be forward. I mean, how is that chlorine going to bond and be back here? It can't be. I mean, if I'm here, and I'm going to bond to you, it has to be this way. If it's the other way, I can't bond to you, right? It's straightforward. This is also forward. And that's the chloronium that comes from this. Now the chloride, the other chloride comes in and attacks, but it pushes this off. But since this is bonded forward, how is this coming in? This comes in back, and when this comes in back, it's coming from behind the board. Pushes this back off, that's going to give what? Which one of these would it give? Trans. another chloride had to come in from the back. And this is the mechanism. Now, again, physics or proximity. Which lone pair? They're both lone pairs. Which one can attack your fastest and easiest and first? Again, this left hand. Here we go. Sorry. Didn't even move before I got there. This right here is bam, it's there. This guy doesn't even have a chance to move before the other one gets there. So that just makes sense that it's going to be there first. Indeed, all your evidence points to this mechanism, and this is the known mechanism, or what it is it's the best theory. Does anybody else have a better mechanism to support the evidence that we have? Well, the answer is no. No chemist has a better theoretical proposition. This is the theoretically most sound mechanism for addition of halogen to an alkene. Yeah? Question?
I was going to ask, is that one you just drew, the last one you just drew, is that not actually formed on the first part before the chlorine joined?
I think I erased it. There's no carbocation in this mechanism.
Okay. The one to the right, before the chlorine joined. It attacks the one that's closer, it attacks, because this lone pair is already there, so it already formed, and the chlorine comes and kicks it off and becomes trans. So before the chlorine comes and kicks off the bond, is that not actually formed?
No, this is your intermediate here.
Okay.
This is called a chloronium ion. This is the only intermediate reaction. I showed that on the other page. Same mechanism. That's the only intermediate. It's a bridge chloronium ion or bromonium or whatever halogen you have. This thing here is just me, Stevens, trying to help you along and see what's happening. Okay? Not actually formed.
Okay.
If you did a reaction coordinate diagram, there's only one intermediate. Again, the first two steps here are concerted. As soon as this attacks, you're back bonding. Back bond over here. This is losing electrons. It would be a cation if it was just free, but it's not, because as soon as it's breaking away, you're here. It's all one transition state, going straight to the one transition state leading to this. This is just me. I think, okay, yeah, trust me, I think it's the best way to show it. A book is not going to show it like that. But I've seen too many students of what's going on here, I don't know. I think this is the best way. But you need to put NAF here. You got to realize this is not actually formed. NAF. If you don't put NAF, then it looks like you think it's actually formed. Okay, we'll do more of that. Because we're under B, right? And B says there's no carbocations. We're not going to form a carbocation with any of the reactions under letter B. Okay, what about F2 or I2? Typically this is only done with Cl2 and Br2. F2 is just too darn reactive. And you rarely see it, or hardly never. Too reactive. Iodine, on the other hand, why is it too reactive? Well, if you do calculations, you'll see that it's quite exothermic when you use fluorine. So exothermic that you better stand back. It may just explode. All the energy coming out. Okay? Boom, bam. Iodide, on the other hand, is too unreactive. And if you do calculations, you'll see that it's an endothermic reaction. It's just not favored. It turns out that Cl2 and Br2 just have the right thermodynamics and are thus the most common for this type of reaction. Sometimes you can see some iodine with a variation. Okay. By the way, some of these have actually been isolated and studied. I gave you a reference down there at the bottom. Next reaction. You've got the green. That what was the number 1 or something? Or number 2, addition of halogen and water to give what? Transhalohydrins. Right here. It's the same reaction, but we're including water. Include water, you're going to get a product with 1 halogen, but the other new group is going to be an OH. A halogen, and this is like it's been hydrated. So it's like halohydrated. It's called a halohydrin. Mechanism here. What's the same up to a point? We're going to form the, remember green, chloronium ion. Alkenes don't react with pure water, but they will react with halogen. This attacks here. Where we leave cation in? So over here, right? We get to this. Is this really an intermediate that's formed, or is something else happening at the same time?
Something else was happening.
Yeah, this over here is going to back bond at the same exact time, right? This is not actually formed. These first 2 steps happen all together, and we get what? Chloronium ion. That's the first intermediate here. We also produce Cl minus. Cl minus can add here, we get a dihalide, but that's not what happens. If you have water, water is going to be the nucleophile. And the water is what attacks. Where are we going to attack, left or right?
Left.
Left. It's the more substituted. It's also the same place we showed cation over here. It's the same place. The only difference is we don't attack a free cation. We're attacking something and kicking off the chloride, the back bond. When this comes in here, it kicks this off. What does that lead to? It's not product yet, but we have boom, boom. We now have it. We now have that. Everybody agree? Now you got to be careful here. At this point, you guys will do this 1,000,001 wrong ways. You got to look at the details here. First off, I'm drawing everything out. We don't just do something like that. Right? I don't know what this is. It looks like water, but I don't know what's bonded to what. I can't tell the oxygen has a positive charge, etc., etc. Okay? What does this arrow mean? A lone pair made a bond to carbon. There it is. Lone pair made a bond to carbon. The other lone pair is still there. The other 2 H's are still there. It's a positive charge now. Clear details here, okay? What do we need to do to get final product? And don't worry about rotation. I've got the OH shown up. It doesn't matter.
The Cl minus comes in.
We need to lose what?
Hydrogen.
Yes. Well, guess what? The Cl over here can actually act as a base and take one of the H's and leave that behind. And what does that give? Well, that gives the product, and it now has 2 lone pairs on the oxygen. But what did we create here?
HCl.
Yes. A byproduct of this reaction is HCl. Now, of course, that you can draw a full Lewis structure for that if you want. I just showed it all condensed. But the H is bonded to the Cl. Now, you could actually have used water to take the H. If you had used water, we would have created what? H3O plus. But guess what? How does HCl exist in water? H3O plus. So you would actually be more strictly correct if you had used water to take the H. But what you need to be able to see is this reaction is going to produce HCl. Your mechanism shows that.
On the final product, you have the OH on top, but on the bottom.
That does not matter.
Doesn't matter.
No. Is the OH attached to the right carbon? In both? Yeah. Well, what you're referring to is stereochemistry. We're going to have to learn when does it matter. It doesn't matter here. Because the carbon is not chiral, et cetera, et cetera. We will start seeing examples where it does matter, but not here. You see, I'm not even showing the tetrahedral nature of that carbon. Okay. Right now, it's just, is everything connected? Is the connectivity right? Note, we are not forming the compound on the right. You expect this to be formed? Not if you know mechanism. Because initially this attacks this way, right? And to me, showing this, which is consistent with our previous reactions, helps you stay on track to getting the right product. Okay? Because the only way to get chlorine over here is for this to have attacked this way and left the original cation there. But tertiary is preferred, right? First question is where will the cation? That's why I continue to ask that question, even though a carbocation is not actually formed. Okay, I'm not going to go on and on about that. Hopefully you get my strategy. This reaction is regioselective. The OH is only going to bond to this site or region. Halohydrin. Okay, let's look down here. Halohydrin, just bromine instead of chlorine. What are we going to get? It's going to be this product. The OH and the bromine are going to be trans. Now we're bringing in some stereochemistry. What's the first thing happening here? Alkenes don't react with water. Alkene react with bromine to form what? Can I just show the bromonium ion? And the bromonium ion is going to have some stereochemistry because the two carbons are now tetrahedral. Let's draw both of them forward. How about that? Positive. There's a methyl here. That methyl would be back. Has to be. Tetrahedral. Two in the plane, one forward, one back. Two in the plane, one forward. There's an undrawn H going back. Right? And see, I'm going to get the enantiomer. But that's okay. We also get an enantiomer. Then the water attacks. Which carbon is the water attack? Top or bottom? Top. Okay, it attacks here, kicks off the bromine. How is the new oxygen going to be bonded here? The bromine was positioned forward, so how does the water come in? Comes in behind. So the new bond to water is going to be back. Okay? And this just gets opened up. There's no change in this bond. Still forward. Importantly though, the methyl though gets pushed forward. That's really, eventually we'll call that inversion. And that's the stereochemical outcome of this water adding. Now we just lose the H. What can take the H? Well, there's a bromide that's formed here. It can take the H. I'm not doing full mechanism here. We've already done a full mechanism. Okay. It can, and when you do that, what do you get?
HBr and that product.
You actually don't get that product
With the
because
enantiomer.
the bromine is going to be forward. Bromine's forward and the water's back. You actually get the enantiomer. But see, you get both because the bromonium ion could also look like this. Both bromines could be back. And that forward. See, when you make when this attacks bromine, it can attack from the front. If it attacks from the front, you get this. But it can also attack, the bromine can be in the back, and all your bonds will be going back. So you get both. But now if water attacks this, it's going to attack the same site, but how is it attacking here? The bromine bond is going back, so this is attacking from the front. And so the OH would be forward, the bromine would be back. OH forward, bromine back. And that would give, and I'm doing multiple lines because there's something there, there's a protonated species, and then you got to deprotonate. That leads to this. In both cases, bromine and OH are trans. That's why it's called a trans-halohydrin. Okay? But we only see that stereochemistry in such an example like this. You don't see it up here because the stereochemistry is not as defined in that type of product up there. When the stereochemistry is defined, the bromine and OH are going to be trans. Because the mechanism tells us that. Okay? But we wouldn't get it both here. We'll see next week in enantiomers. These are just mirror images. It's like this reaction, we're making hands. And I'm telling you, we're going to make a right hand. We're also going to make a left hand. I'm saying we're going to make this plus the other hand. I just didn't show the other one. That's how this is. We're going to make the right hand, and I'm telling you, we're making the other hand. Again, that's coming next week. Predict products down here. You can do these on your own. We'll start looking at these when we got time. The first step with any of your reactions is, what type of product we're making here? An alkene with halogen and water. What is that going to be? Halohydrin. Okay? When you first look at a reaction, you just got to know what type of product it's going to be made. Then next comes, okay, what's the mechanism for making this halohydrin? You have your mechanistic thought. And eventually then we'll have, what's the stereochemical outcomes going to be in these reactions? And we'll have that thought. Okay? That's actually just, there's no water here. There's halogen, got some stereochemistry here. Remember deuterium? One of the first handouts I gave you? It's just a fancy hydrogen. Okay? Anytime you see something deuterium, it's the same exact chemistry as this, that was HCl. It's just a fancy H. But by it being D, we can focus some more on stereochemistry. It gives us stereochem. It makes the product stereogenic. So instructors sometimes use D instead of H. The chemistry is the same. Okay. Next, and by the way, we're working our way around the dial. Yeah? We did trans-dihalide, we just did trans-halohydrin. What's next? Epoxide, yes. That's also Roman numeral 3. Yeah? Okay? And we have it here. Epoxide. An epoxide is a 3-membered ring with oxygen. That's a cyclic ether. It's actually a cyclic ether. Gets its own name, epoxide. These can be made and isolated. We react the alkene with a reagent. It looks like this. This is condensed down. It's called a peroxy acid. We showed full structure like this. If there was only one O over here, that was just OH like that, that is what type of functional group?
Ester.
Carboxylic acid.
Okay. It's like a carboxylic acid that has the additional oxygen there with a peroxide. An OO bond is called peroxide. And this is called peroxy acid. All right? Condensed down to look like that. 3 oxygens instead of 2. The most common peroxy acid is MCPBA, which is metachloroperoxybenzoic acid. Should be in your textbook. Here I'm showing just generically. The R group can be just about anything. Most common is the benzene ring with the metachloro. Okay. In the peroxy acid, you got 2 oxygens. Somewhat analogous to having 2 bromines or 2 chlorines. Now this is more reactive because it's a weaker bond, etc. But this will still react. Which oxygen is electrophilic? Which one does the alkene attack? The one on the end. Because if you look at polarity here, the carbonyl is pretty polar. That leads to a dipole. And it makes all the electrons sort of move that way. And this terminal oxygen is the most partial plus. So this attacks that oxygen and kicks the other off. Just like attacking bromine and kicking the other bromine off. What does that give? It gives us here. Now bonded to that OH. Bonded to the OH. That got kicked off. That's what got kicked off, right? Now, what do you think is going to happen here? Is this going to be a true cation, or is something going to happen very quickly? This is going to back bond, and the back bonding occurs. The back bond is occurring right here. As soon as these electrons are coming out, these are coming this way. But you see how I show it, right? So this is not actually formed, and when it back bonds, what do you get? You get that 3-membered ring, analogous to like the bromonium ion. But guess what? This can be isolated by just removing the H and going neutral. What can take the H? Well, that leading group up there, the thing that got kicked off. If that takes the H, it's just an acid-base reaction, yeah? Leave the electrons behind, what does that give? There you go. And that can be isolated. See, the difference is, one difference, the bromonium, there's no H there, and it can't go neutral. The only way for this to go neutral is for something to attack over here, and it gets those electrons back. So you get other chemistry. Here we can go neutral by an acid-base, deprotonation, you get this product, and it can be isolated. Called an epoxide. And then the fate of the other thing is there. The important thing is to see the similarities in the previous reaction. And so it's not like a brand new reaction. Our reactions are going to have consistencies, similarities. Yeah? You can try these on your own. I mean, the first one pretty darn easy. You show the product of the first one? Why don't you maybe look at any and all of those while we take a short 2-minute break. Well, you got 6 carbons here, there's only 5. It should make sense. I'm not so sure exactly what you're referring to, but it doesn't make sense. Cations in the wrong place. When the alkene attack, where you going to leave cation? No, cation is not there. instead of showing all pairs, show the bonds. Which you have a little bit. Okay, I see a couple of you trying to do the very first one and having difficulty just showing the first intermediate, or the NAF intermediate. One thing you have to do in your studying is you can't just watch me do it, you have to do it. Everything we've done before, you need to go back through and do it yourself, but then look over here and see if you got it right. You can't just look at what I did. You have to do it. You just look at what I did, everything looks groovy. But then when you try to do it, uh-oh, I can't do it. You've got to immediately get to, uh-oh, I can't do it, and then figure out how to do it. If you wait until the test day and figure out, uh-oh, I don't know how to do it, you're going to be in trouble. You got to do it yourself. Even the stuff that we've already done. MCPBA, basically it's an example of that, right? The R group is just a phenyl with a chlorine. These electrons attack this oxygen. Kick that one off. What does that give? Boom, 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 boom. Here's the carbon. These electrons wouldn't attack oxygen, so this bond is now here. And that oxygen has an H, and that's it. Everything else got kicked off. There are two lone pairs there that did not get kicked off. That's it. That's a positive charge here. But many of you just cannot do up to this point. You got to realize that you're going to have to figure out what we're doing here, and I've tried to explain it. This just went over and it made a bond. I'm now showing that bond, what it bonded to, but this is left as a carbocation. Okay? Is this actually formed? By the way, I'm doing mechanism here. That's good. You can almost just predict product once you get good. I mean, the product is just what? Boom, 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 boom. These two carbons now have an oxygen there, and that's it. I mean, everybody recognize that? I mean, made epoxide. The two carbons of the alkene now bind to one oxygen and they say epoxide. You got to recognize that, okay? But that's just sort of memorization. It's okay. There's a little bit of memorization in organic chemistry. But then immediately your mechanistic knowledge has to kick in. Because you may be asked to show a mechanism. Or you have to use mechanism to predict stereochemistry. That's just very simple up there. Well, mechanistically, this back bonds, right? I mean, when it back bonds, we get to, well, again, this is bonding to oxygen. I can show it here. It's got to move closer, so I'm going to make this bond angle more like this. But when it back bonds, what does this mean? This arrow has to mean something. What does it mean? WDAM. What does arrow mean? It means the lone pair now made a bond here. There's one lone pair left, and there's also an H here. And that's a positive charge. And this is not actually formed, because as we've talked about, and I'll say it this way, anytime the new thing has a lone pair, the lone pair is going to back bond immediately, and this is not actually formed. Here's your first intermediate. What happens from here? The thing that got kicked off is going to take the H. I'm not going to do it here, but when it takes the H, there's your product. Okay? You've got to work through these mechanisms and convince yourself you can do it. All right. Does someone have the second one? Anybody got a product for the second one? Because the second one, when you have a ring, it's easier to show the stereochemistry. And so my first couple of examples are going to be rings. Eventually we'll go to non-ring stereochemistry, and that's a touch more difficult. Anybody got your second thought? Second. If we do not show stereochemistry, that's the product, right? And if I can connect my bonds, that's a three-member ring. Is that it there? Everybody agree? What's going to be the stereochemistry of that? Because these two carbons are tetrahedral. Two in the plane, one forward, one back. The stereochemistry is going to be, if we put that back, we can put this bond forward. If that's forward, how's the other bond? Forward. It has to be forward. And so this is shown generically with no stereochemistry. This is stereochemistry. But we're also going to get the enantiomer. Enantiomer there. You can just put that in your notes for now. The enantiomer is just a mirror image. And the mirror image is where all your projections are reversed. All your dashes are changed to bold, all your bolds are changed to dashes. Right now, that's just sort of a prelude to that. Now, these two are a little bit more difficult. Stereochemistry here. But if you ignore stereochemistry, it's easy. You're just going to connect an oxygen to both carbons of the alkene. Next. Cyclopropane. You can also make a three-membered hydrocarbon ring. Cyclopropane, right? We can make this using a carbene. Carbene. In this case, this is called diazomethane. One carbon methane, and it's got two nitrogens, diazo. Okay. It's a toxic explosive gas. We will not be doing this reaction in labs. Okay. Lewis structure like this. It's got two formal charges, but it's net neutral. It's a neutral molecule. All right. Now, if you heat this, it will break apart. These electrons move on to nitrogen. The bond is broken, but that's nitrogen gas. Yeah? What we're left with is just the CH2 with a lone pair. Now this is driven by entropy, one molecule going to two. Like if I broke a coffee, and I dropped a coffee cup, one cup would go to 100 pieces. This is just, okay, sort of favorite here. So that's an argument for why a little bit of heat, this will go. Problem is it'll go pretty easily. And if you got a lot of it and it goes real easily and fast, you've got an explosion because you have a lot of stuff. Okay? One molecule going to two, and so you have an increase in pressure and stuff. Okay, let's focus in on this. This is called a carbene. Why do I have two charges there? It's net neutral. Some people will show this with just no charges because it's all neutral. How can the carbon be both plus and minus? Well, this is sort of bookkeeping and reinforcing the fact it has dual character. It has carbocation character, but it also has lone pair character. True full structure of this would be, I think there was actually a carbene on test 1. Okay? It's actually, remember how we said is that a standard carbon? No, that's not 4 bonds. And I said if it's not standard, it's probably going to be charged. Well, this is an exception. That's a non-standard carbon and it's not charged. It's actually neutral. It's called a divalent carbon because it's got 2 bonds, divalent. It's called a carbene. Carbenes can be made. One way to make them is from decomposing diazomethane. Hybridization of this carbon. I can't remember the question on test 1. What was it about?
What it was charged, what the charge was.
Charge. Okay, it was on page 1. Yeah. How about the hybridization of this carbon?
Yes,
That's what he took.
sp2. If you graphed it, you would see it has an empty what? It has an empty p orbital.
Yeah.
Does this carbon have an octet? No. Carbenes do not have an octet. It's electron poor. Do you think it would like for electrons to come in here?
Yes.
Yeah. Electrons attack it and fill the orbital. It's reactive. What electrons can attack it? The electrons in the pi bond. It's almost like it's attacking the positive portion. And if it's attacked, what would you get? You make that bond. But the carbon has a lone pair. What do you think it's going to do?
It's going to bend.
And immediately. See, this is not actually formed. And when it back bonds, what do you get? There's your product. You don't even have to remove a proton. How many intermediates in this reaction once we form the carbene from here to there?
No.
There's no intermediate. Here we go. You're a carbene. You're a carbene. As soon as I attack you, you're going to back bond. There you go, cyclopropane. It's just one transition state. Again, this is just me on the board trying to illustrate, keep it consistent, yeah? That's it. After you make your, see the consistency so, previous reactions? Okay. Now, you can also make carbenes, or you can make cyclopropanes that have 2 chlorines on them. Or 2 bromines, but 2 chlorines is most common. And this can be done a little safer. You don't have to use an explosive gas. This is chloroform and hydroxide. And we can generate a carbene here. Chloroform is slightly acidic. And hydroxide can act as a base. All right, do acid-base mechanism. That'll lead to this here. At this point, though, the carbon is minus. Chlorine is like, hey, carbon, I know you don't like being minus. What if I leave? And if these electrons just leave, what do we produce? We're going to make this dichlorocarbene. Indeed, it is. Because only when that leaves, you just have 2 bonds and a lone pair. 2 bonds and a lone pair. It's just like that over there, except it's just 2 chlorines instead of 2 H's. Why does this happen? Well, one molecule going to 2. That's an atom, but okay. The other thing is, instead of the carbon being minus, chlorine is now minus, and that's better, right? Doesn't chlorine prefer to be minus compared to carbon? And that's actually net neutral. I'm just showing these dual charges because it's kind of helpful. Well, then you can have your alkene attack, and then the back bonding, and then there you go. You make a dichlorocyclopropane. These are easier to make in lab because chloroform and hydroxide are safer than diazomethane. You need to have the chlorines there because if this didn't have chlorines, it wouldn't be acidic enough to do the chemistry. So that's reacting with carbines. We call it chloroform, right? That's a common name for trichloromethane. Chloroform, it's a solvent, a little bit toxic. It actually used to be used as a anesthetic or sedative. Queen Victoria made it sort of famous whenever she used it during childbirth or was given chloroform to sedate her during childbirth. It became used as a sedative. The problem is it's a little bit toxic and some people didn't wake up. There's a narrow threshold between being an effective drug for sedation versus being permanently sedated. And eventually it was replaced by other, better, safer anesthetics. But 200 years ago, they didn't have any way to sedate someone. They want to cut off an arm or amputate, want to knock someone out. What else did they used to use 250, 200 years ago?
Cocaine.
Perhaps. Civil War. What was big before chloroform? Ether. Diethyl ether, especially during the Civil War. To sedate someone, to kind of knock them out. Get them to where they're almost unconscious so they can perform some surgery. But ether problems too. Imagine the headache of that. But ether and chloroform used to be used as anesthetics. Sedative. Okay. Actually, a lot of drugs contain cyclopropane rings. Here are some examples. So even though it's a strained three-membered ring, it's still pretty prevalent. Can be made, and it exists in a lot of drugs. Unusual number of drugs there. Yep. Carbines. Might see in biochemistry or something. Here's a drug that's being oxidized in the body, and when it's oxidized, a carbene is being formed. And so there's a little bit of application of where you may see carbene somewhere else. But carbines can also be reactive. Okay, oxymercuration. Looks like we've made it to Roman numeral 5, B5. Bingo. Okay, oxymercuration, alkoxymercuration. I think we looked at where have we made it to? We've actually made it all the way around. We've got 2 more to go. Both of these reactions to go, both produce alcohols from the alkene. Convert to an alcohol. The difference is regiochemistry. Oxymercuration, the OH is going to end up the more substituted carbon with hydroboration, oxidation on the less substituted carbon. These are other ways to make alcohols. Remember we made alcohol up here by hydrating the alkene with just aqueous acid. Down here we're using other reagents. Oxymercuration. Okay, you take this alkene, if you hydrate it with aqueous acid, you actually get this as the major product. Because what? Actually a hydride shift. Okay? Carbocation. Carbocation rearrangement. Right? What if you wanted the OH here though? You can do that using this here. Mercury acetate and water followed by sodium borohydride. Does this reaction involve a carbocation intermediate? No, because what? Thought the answer was going to be because we're under B on the outline, and every reaction under B on the outline does not contain a carbocation intermediate, right? Right? Aren't we under letter B? None of the B reactions contain a carbocation. Since there's no carbocation, guess what? You will not get any rearrangements. You only get rearrangements when a carbocation is formed. Skeletal rearrangements. Okay? So that's why the OH is sort of on one of the original alkene carbons.
So the top thing is not,
Do what?
the top one is not carbocation at all.
Right. You do get that, which is aqueous acid. Standard hydration. This is a specialized hydration, no rearrangement. Let's see how this reaction works. First thing is mercury acetate. We could show this different ways. You could show this Hg. What's the charge of the mercury? What's the charge of the acetate? What? What's the charge, if we show it ionic, what's the charge of the mercury? Positive what? What's the charge of the acetate? -1. There's two minuses. This is 2 plus, right? Acetate. Everybody knows acetate? You should know acetate. -1. Okay. Mercury 2. We can show this fully covalent, whatnot. I'm going to show an Hg with 1 acetate, and the Hg would be what charge? It would be plus. Okay? This is where it's sort of monoionized. I mean, it may be fully ionized, but let's just show it like that. Okay, and 1 acetate. Hg plus, that's a lot like an H plus. Double bond attacks the mercury plus. What does that give? Don't. Mercury acetate. What's on this carbon now?
It would be a plus.
Carbocation. I mean, if we just do that arrow, then you should give this. But is a carbocation really formed? No. Mercury. The mercury has at least 1 lone pair. And since it has a lone pair, what's going to happen here? This will back bond, right? And when it back bonds, what do you get?
And this ring.
You get this 3-membered mercury ring called a mercuronium ion. What do we need to show here? Is this really formed? No, this is NAF. Anytime you back bond, that happens at the same exact time. This is not really formed. The first intermediate here is your mercuronium ion. Okay? You have water here. Water attacks. Which carbon are we going to attack? Top or bottom? Bottom. It's the same argument. This is going to strain, just like a bromonium ion. If it strains, which carbon is going to take on more partial plus? The one with a rich friend. It's the same answer as over here. That's where we're going to attack. But instead of attacking a free cation, we attack carbon and kick something off. In this case, what are we kicking off? We kick off the mercury. And when that gets kicked off, what do we get? Mercury gets its lone pair back. What's now bonded to this carbon over here? O, but it's got two H's, one lone pair, and that's a positive charge. This needs to go neutral, and it can. What can take the H here?
The mercury.
Won't be the mercury. There's something else on the board that can take the H.
All the other acid.
The other acetate. The other acetate can come in here and act as a base, bond to the H, take the H, these electrons stay behind. And what does that give? Gives that plus what? It gives that product plus acetic acid. You put a proton on acetate, you have acetic acid. This is end step one. That's what you have after step one. This is a two-step reaction. This happens first, then you come in with this. Remember line reaction? 1, 2. What do we need to do to this to get to final shown product? Not up there, right here. What do we need to do to get to that? We got to get rid of the mercury. You're actually replacing the mercury with something. What do we need to replace the mercury acetate with? How many H's on this carbon? 2. How many H's there now? We need to replace the mercury with an H. But it's not H plus. It's H minus. And this here is an H minus source. What do we call H minus? Hydride. Remember we did hydride shift? Yeah. This is called sodium borohydride. Lewis structure. It's a boron with 4 H's. What's the charge of the boron? How many does it own? It owns 4, but periodic table says it's only own 3, so it's got an extra one that charges negative. You got to have a positive with it. Sodium or potassium or something. That's called sodium borohydride. We'll see this lots in organic too as a hydride source. I say it's like shooting darts here. See, that boron is not happy, it doesn't like being minus. So it tells the H and its electrons to take a hike. It starts throwing H and it starts throwing hydrides. Serves as a hydride source. Now I'm not going to do kind of full mechanism here. This is probably not correct, but if we had a hydride, which was delivered by that reagent, if these electrons attack here and kick that off, what would that give? That would give product. But now H is on there. So we need H and electrons. You don't need H plus, you need H hydride. But tell me, okay, that's the product. There's no rearrangements because we never formed a carbocation. The main intermediate over there was the mercuronium ion, which is similar to a bromonium ion, etc. Tell me the fate of the mercury. What's the charge of the mercury now? What does it look like? What should be the charge of the mercury now? Charge of the mercury here. What does this arrow mean? Taking on. If it had one to begin with, it now has two. If that's neutral, it only owns one of the bond. Now it owns two from the lone pair. What's the charge of the mercury?
It's negative.
It's now negative. Well, guess what? At this point, the acetate will leave, and you'll produce mercury plus acetate, and it becomes negative. But what is this here? That's neutral mercury atoms. It's elemental mercury. This reaction produces elemental mercury. Because of that, it's not used as much anymore because elemental mercury is considered an environmental pollutant. Okay? We don't use mercury thermometers as much anymore, et cetera, et cetera. Key thing is here, I assume you guys can see over there in the shadow. If not, please let me know. Key thing is here, can you follow the electrons and see that it's mercury at the end? That's the important thing here, is following the flow of electrons and how we move them. This is called, what's it called? Oxymercuration, because what do we do first? Well, right here. Here's the oxymercuration. Our alkene has oxygen, oxy. It also has a mercury. So we oxymercurated it. But then what do we do next? What's the second step? That can vary, because if this is an OR, it's an alkoxy. That can vary. Instead of using water, you could use an alcohol. But what do we do next? Reduction. Whenever you add H's, that's a reduction. Thus, sodium borohydride is known as a reducing agent because it supplies H's. Okay. In Gen Chem, you looked at reduction as gain of electrons or something? And oxidation as loss of electrons? In organic chemistry, it's more common to look at a different way. Adding H's is considered reduction, loss of H's is considered oxidation. All right? There's one other way that we'll talk about later. So, oxymercuration followed by reduction with sodium borohydride. It gives an alcohol, and this is called the standard product, or Markovnikov product. We'll clarify that later. Another way to make an alcohol is by hydroboration oxidation. And this method gives an alcohol, but it's the opposite regiochemistry. Here the OH is going to be on the N carbon. Okay. Here we can react the alkene with BH3. It's called borane. What hybridization do we expect for borane? It's a neutral boron. There's no lone pair. sp2 with empty what? With empty p orbital. Okay, there's no octet. It's got an empty orbital. It's thus electrophilic. Even though it's neutral. It's not was to a carbene. A carbene is neutral, but it was attacked. This can be attacked. These electrons will attack the boron, and what will that give? Bond to boron. Where was the cation at? Top or bottom? I should have asked that first. Bottom, correct? Okay. Cation here. May bond to boron. Let's draw in these H's. It's got 3 H's. What's the charge of the boron now? Negative, right? We just saw a negative boron before with sodium borohydride. Okay, do you think this is actually formed?
No.
Why not?
Because it's a negative price.
Why? There's no lone pair here. I thought you were going to say because we're under B in the
There's no carbon.
outline. So there's no carbocation. It's not. But this is a little bit different. Everything else we had a lone pair before. This is a lot like hydride, sodium borohydride. The boron's not happy. It's going to shoot H's. Well, guess what? It shoots an H over here. It's a hydride shift. One of these hydrides breaks away from the boron and moves here. We've done hydride shifts before, but those were 1, 2. What is this? If that's 1, where does the hydride end up? Not 2, but 3. It's actually a 1,3 hydride shift. See how that looks like sodium borohydride? Once it became minus, it became a hydride donor, or shooting these hydride donors. What does this give? Boom, 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 boom. BH2 now, that's neutral. Gives that, right? I don't know whether to draw the H or not. Let's look at this carbon here. How many H's here? 1. How many here? 1. How many here now? 2 H's there. How about that? Right? And it's neutral. That's just a plain old CH2 group now. This is N step 1. And what do we do to the alkene? We got a hydrogen here and a boron there. We hydroborated it. We did a hydroboration. Alkenes will react with borane to give such a product. It's basically reacting with the alkene, or the alkenes reacting with it. If you want to, this is the thing that's the electron. Question, is this actually formed?
No.
Not actually formed. Because as soon as, see here it's not a lone pair, as soon as I attack you over here, now, you're going to throw an H. Not a lone pair, but you're going to throw a dart over here. Here I come. Doop. There we go. Bond to boron, and there's a new H over there. One transition state. Right? Not actually formed. Boom. There's no intermediate hydroboration. There's actually no intermediate, is there?
No.
No. It just goes from that, one transition state, here you go. What do we need to do to get the final product? We need to replace the boron with what? OH. Indeed we do. Well, that's what this does. It replaces B with OH. Okay?
The end of a step isn't considered an intermediate.
Do what?
The end of the step is not considered an intermediate.
I didn't hear you. What's not considered an
The
intermediate?
end of the step.
Well, step one is a step. There's no intermediate in step one. It depends on what you mean by intermediate. There's no intermediate in the mechanism leading to that product in step one. Now, overall, the two-step sequence, you may call that an intermediate to two-step sequence. So you've got to clarify what you mean by intermediate. Replaces that. And this we're not going to look at a mechanism for, but this is magic. Okay? Or do you want mechanism? Be good if you want it, because you should be thinking mechanism. But magic is not good. If it's just magic, we just memorize and that's it. Part of what we're doing here in organic chemistry is we're learning how this takes place, mechanism. But that one we're not going to look at. It's too off the wall. I don't want to take us there. Can we just call it magic?
Yes.
Okay? It magically replaces the boron. Important though, no change in stereochem. Whenever it replaces it, there's no change in stereochem. Once we start doing stereochemistry, whenever we do that magic step, there's no change in stereochem. We'll refer back to this later. And that's how you get the product, the OH out here, which is sort of a non-typical product. Because if you base everything on cations, cation here and water attacks there, the OH should be bonded here. So how does it end up bonding out here? Well, that's kind of odd. That's the atypical product. That's called the non-Markovnikov product, or anti-Markovnikov product. The atypical product. See, if this could not rearrange, these would give the same products. The only reason this is different is because that can rearrange. Here we're doing it standard kind of product, but no rearrangement. Down here it's the odd product. How does the OH get out there? Well, it's hydroboration oxidation leads it to being out there. Okay? So this is an isomeric alcohol called the non-Markovnikov alcohol product. Now, books will tell you that in this case, the OH is bonded to the least substituted carbon. Well, that's true. Some books will also tell you that the new H is bonded to the most substituted carbon. Well, that's true. I mean, you can memorize it however you want. I present it as it's sort of the odd product compared to standard hydration. How does the OH get out there? Okay. So we have an alkene. You can do these here. Okay? We'll look at these on Monday. You can also start thinking about stereochemistry with the ring here. There's a procedure for doing an oxymercuration. I'll read the actual procedure. You can find procedures like this online, organic syntheses. But any reaction we ever talked about, you can find an exact procedure, get the details of it, how to do it. These also tend to be pretty large scale, it's almost 100 grams. One thing I didn't say over here is BH3 can exist as a dimer, B2H6. If you ever see B2H6, just consider it BH3. That's just a dimer form, but it's the same thing. It's in equilibrium between the monomer and the dimer. All right. Over here is a synthesis, multi-step synthesis that includes a hydroboration oxidation. Going from 7 to 8. There's also another variation. They're using something called 9-BBN. Just mark that out and change it to BH3. There's a couple other boron reagents that are used in place of BH3. I'm not going to discuss them. Your book may or may not. But 9-BBN is just an alternative to BH3. Same chemistry. Except instead of H's on the boron, there's just other things there, but it doesn't change anything. So what are they doing here? First off, you see this is a hydroboration followed by an oxidation. What is the oxidation? That's hydrogen peroxide and base. And hydrogen peroxide is an oxidant. What are they doing here? Right here, right? Here's your alkene. Where's the OH going to end up at? Top or bottom carbon? Well, let me ask you, where would the cation be formed if you made a cation? Top or bottom? Bottom would be the cation. And if water attacked there, that would be the standard product. But we know that hydroboration gives the non-standard. It's going to end up attacking and bonding up here. The OH is going to be bonded up there. And indeed, look at the product. The OH is bonded up there. Now they do have some stereochemistry, which we're not able to discuss at this point. But in terms of regiochemistry, the oxygen is bonded to that site, not to that site. They're doing a hydroboration oxidation. Okay? Now, along the way, I give you a number of these, and whenever I handwrite in the reaction, these are reactions we'll eventually look at. Okay? That's organic 1, that's organic 1, that's organic 2. This is organic 1, okay? Michael addition, that's organic 2. All right? So even if you don't have any for organic 2, you can keep these as reference for later on if you can keep up with it. But I'll give you others as we go along. Okay. How are we doing, guys? Let's see what we need to do to finish up today. Any questions? We're good to go? Monday, you turn in your literature assignment? Is that right? Your crystallization lab? Okay. We have lab lecture. We'll have lecture during lab time on Monday and Tuesday.
The ones that aren't found on this worksheet, we didn't figure it out. It's not that you can't find it there, it's that it doesn't exist. It doesn't say anything about that.
How about what?
Okay, guys, have a nice weekend.
Well,
Have a good weekend, guys.
So, when you look at this one, but it doesn't have this one. My back impression. Like these two, that I picked out as weird ones, were tested under 1, 4, 5, 4, which are different guys. Whatever, they stuck it basically in the back of the Yeah.
I did fair enough.
But not.